Every single time you search for something online or get directions on your phone or even just stream a video, you're using algorithms. You can think of them as these invisible recipes that are just powering our entire digital world. But here's the thing, not all recipes are created equal. And that leads to this just fascinating question, which Claudia Reid puts perfectly. I mean, if these things are just recipes, why do some of them run in milliseconds while others would literally take longer than the age of the universe? How is that even possible? Well, that's the mystery we're going to try and solve today. Okay, so to get our heads around that massive cosmic scale question, let's bring it right back down to Earth. Think about it. You can't really measure a recipe's speed with a stopwatch, right? It totally depends on the cook, the kitchen, the oven. So how on earth do we measure an algorithm's speed in a way that's universal? Something that doesn't depend on the specific computer it's running on. All right, so first things first, we've got to get our terms straight. We're about to tackle what sounds like an impossible problem, so we absolutely need to define our tools before we dive in. So what is an algorithm, really? Well, at its core, it's just a set of step-by-step instructions for solving a problem. The recipe analogy is perfect. You take your inputs, your flour, your sugar, and you follow the steps to get a very specific output, a cake. The key here, and this is super important, is that every single step has to be crystal clear. No guesswork allowed. Okay, now for the next big piece of our puzzle, how do we actually measure the speed? To compare all these different recipes, we need some kind of universal system. And in the world of computer science, that system has nothing to do with seconds or minutes. Nope, it's about something much, much more fundamental. It's a concept called time complexity. And here's the absolute crucial point, so listen close. We are not measuring time in seconds. We're measuring growth. We're asking a different question. We're asking, hey, if we double the amount of stuff we have to work with, our input, does the number of steps we have to take also double? Or does it quadruple? Or, and this is where it gets really cool, does it barely even change at all? And the tool we use for this is called Big O notation. You can literally think of it as a universal ruler for measuring an algorithm's efficiency. It's a way for us to cut through the noise and focus on what really matters for performance, especially when the size of our input, which we just call n, gets ridiculously huge. Now, I know Big O notation sounds kind of scary and mathematical, but trust me, it's really all about simplification. There are basically 3 simple rules. 1, you look at all the parts of your algorithm and you just focus on the one that grows the absolute fastest. 2, you just drop all the other, less important terms. They don't matter in the long run. And 3, you drop any constants, any simple multipliers. All we care about in the end is the general shape of the growth. And what's so cool about this is that it creates this clear hierarchy, like a league table of efficiency. At the very top, you've got O1, or constant time. This is the holy grail. The amount of work never changes, no matter how big the input gets. Then you have O log n, which is just spectacular. You can have a massive input, and it only takes a few extra steps, just like finding a word in a dictionary by splitting it in half over and over. But as you go down the list to On, and especially On squared, whoo boy, the work starts to grow way, way faster. Okay, theory is one thing, but let's make this real. Let's see this in action with a little story. We'll call it a tale of 2 searches. The problem is simple. Find one specific number in a really, really long, sorted list of numbers. So, our first contestant, let's call it linear search. It's the straightforward, kind of brute force approach. You just start at the beginning and check every single item, one by one. Simple, but slow. Our second contestant is binary search. This one is way smarter, way more clever, but it has one very important rule. The list has to be sorted first. Its strategy, jump to the middle, see if the number is higher or lower, and then just throw away half the list. It does this over and over. So let's pull out our Big O ruler and measure these 2. And the difference is, it's absolutely staggering. Linear search is O of n. That means the work grows in a perfect straight line with the number of items. You double the items, you double the work. Simple. But binary search? It's O of log n. The growth here is so incredibly slow. If you double the number of items in your list, you only add 1 single extra step. Just 1. So what does that actually mean in the real world? Okay, picture this. You have a sorted list with 1 million items. Linear search, in the worst case, is going to take 1 million steps to find your number. And binary search, how many steps do you think it'll take? 100,000? 10,000? Nope. It will take a maximum of about 20 steps. Seriously, that is not a typo. 20 versus 1 million. That's the power we're talking about. And look, this isn't just some weird trick for searching. These same principles, this idea of efficiency, it applies to all sorts of problems, like sorting a jumbled list of items into the right order. And you guessed it, the recipe you choose to do that matters a lot. On one side, you've got something called bubble sort. It's easy to understand, but it's painfully slow. It's O of n squared. That means it's basically comparing every item with almost every other item. It's a mess. But on the other side, you have something elegant, like merge sort. It's O of n log n, which is way, way better. It uses this brilliant divide and conquer strategy. Split the list in half, sort the two halves, and then cleverly merge them back together. This is the kind of smart thinking that makes all of our modern tech possible. So we've seen it, right? Choosing the right algorithm can literally be the difference between 20 steps and a million steps. And this fundamental distinction between fast problems and slow problems, well, it leads us directly to the single biggest, most famous unsolved question in all of computer science. And yeah, there's even $1 million prize waiting for whoever solves it. Okay, so to understand this question, we need to know about two classes of problems. First, there's class P. The P stands for polynomial time, but you can just think of it as the fast club. These are the problems that we consider solvable in a practical sense. If a problem is in class P, it means we have a known, efficient algorithm that can find the solution from scratch, no problem. Then you've got class NP. Now these are the tricky ones. These are problems where finding a solution might be incredibly difficult, but, and this is the important part, if someone just gives you a potential solution, checking if it's correct is super easy and fast. The Sudoku puzzle is the absolute perfect way to think about this. Solving a hard Sudoku from a blank grid, that can take you ages, right? It's tough. But if I hand you a finished Sudoku grid, you can check if it's a valid solution in just a few moments. Easy to check, hard to solve. So here it is, the $1 million question. Does P equal NP? In plain English, is every problem that's easy to check also secretly easy to solve? I mean, your gut feeling, your intuition probably screams no way, right? Solving a Sudoku is obviously harder than just checking one. But the crazy thing is, nobody has ever been able to mathematically prove it. And that is the great unsolved puzzle at the very heart of computer science. All right, let's zoom back out and bring this all together. We've gone from simple recipes all the way to $1 million question about the nature of problem solving itself. So, what's the big takeaway here? What does this all mean? Why should you care about any of this? Because simply put, efficiency is the line between what's possible and what's just a dream. It is the literal difference between a GPS on your phone finding the best route in a second and one that would still be calculating long after we're all gone. This constant hunt for better, smarter algorithms is what takes problems that seem completely unsolvable and turns them into the everyday technology that honestly feels a lot like magic. This pursuit, this drive to find the perfect, most optimal recipe for a problem, that is the true engine of innovation. It's what pushes the boundaries of what we can achieve, whether that's discovering new medicines, designing new materials, or exploring the cosmos. So I'll leave you with this question. What seemingly impossible problem is just waiting for the next great algorithm to come along and solve it?